is Brachiopod shells, and pretty much looking at how their how the structure changes and how that affects their mechanical properties. So, to those of you who may not be familiar to what is a brachiopod, and I personally wasn't until I started working on them, these are the animals that we see here. So they look pretty much like mollusks, but they're not mollusks. They are a different phylum, and but they're similar to mollusks in that they're also sessile marine invertebrates, and they also have two shells that are hinged at the end. But again, it's even though they may to the eye they may look similar, they're a completely different phylum. Now, what made me interested in brachiopods at the beginning is because there are two orders of brachiopods, which are the lingually the Discinisca, which make shells out of calcium phosphate. And this is unusual for invertebrates, especially marine invertebrates, which tend to use calcium carbonate, which is the case of the other orders of the brachiopods. So that's why I started looking at them. In some ways, at least the mineral phase is the calcium phosphate. I worked a lot on bone, so I thought that it would be interesting to look at them. This is the Discinisca tenuis shell, so that's what we see here. And that is the animal that the shell that I've been studying. We have here a scanning electron microscopy image of a polished section of a brachiopod. You see here the two valves of the shell. They're very thin, a couple of hundred of microns in thickness, sometimes even less. They have quite a lot of organic. So the mineral phase, which is in their case, it's francoline, so it's carbonated substituted fluorapatite. It's about 65% weight percent of the shell. And the organic phase is 35 weight percent, which is mainly chitin proteins and glycosaminoglycans. Now, what struck me when I started working with these shells is that they're hard. You can break them quite easily because they're very thin, which is pretty much what you expect from this kind of material. But and then when you look at their structure, we don't discern any kind of structural motifs as you'd see on mollusks. So I have here two scanning electron microscopy images where we can see this is across the thickness of the shell. And we see that it fractures differently depending on the region, but it looks pretty much homogeneous. And this is also reflected when we look at it in higher magnification, where we can see that the mineral has a kind of a granular structure, but we cannot discern any kind of patterns like we see the nacre, for example, which is made of plates, or the cross-lamellar, which we have these slabs of calcium carbonate that are specially oriented. It's only when we look at the shell at very high magnification, and this is a scanning transmission electron microscopy image of a shell, that we see that the structure is composed of francolite bricks, which are the bright regions, and they're about 25 nanometers thick and about 100 nanometers long, and they're embedded in a network of organic material, which is the dark bits in the image, which is mostly chitin. So this is what the nanostructure of the shell actually looks like. Now, what struck me with these shells is that when you soak them in water, they become very flexible, and to the point that we can fold them in two and they don't break. And this is what we're looking at here. So this is one valve of the shell. Oops. It's one valve of the shell. It was soaked in water for a day, folded in two, and then embedded in resin and polished. And this is what we see how it looks like. So in that sense, I mean, it's quite different, even though from other biominerals. I mean, mollusks don't do this. Of course, they have much higher mineral content, much lower organic content. But then again, if you think about bone, which is also made of calcium phosphate, have kind of similar organic and inorganic contents, it's not flexible to that extent. So what we decided to do is to try to understand what is it that water is doing to the structure of the shell. I mean, it's clearly an effect of water absorption. It's changing the structure in some way that is allowing the shell to bend. And this is what we set out to find out. So how is water changing the shell structure and making it flexible? So at first, we resorted to Ptychographic X-ray computer tomography, which we already heard a nice explanation from Virginie. So just to recap, what we're doing is that we're placing the sample on a stage. This stage is going to rotate, and we're going to illuminate the sample with an X-ray beam, and we're going to record a coherent diffraction pattern, and we're going to raster through the sample. And later on, what we do is that we use these diffraction patterns to reconstruct what the image, what the object actually looks like in 3D. So what we did was to cut a small piece of the shell in a kind of a cylinder, which is what we see here. We mounted it on the stage. And then we had 3 different samples, one that was vacuum dried, one that was exposed to 70% humidity, and one exposed to 100% humidity. And what we see here is one slice from the 3D reconstruction that was taken from the middle of this cylinder here. And what we see is an electron density map that is going from 0.63, which is the yellow, all the way down to 0.4, which becomes white. Now, the higher the electron density, we're talking about a mineral, so it's francolite, which has a higher electron density value. And the lower the electron density is an indication of organic, and in this case also water. What we see is that in the vacuum dried shell, the electron density is pretty much homogeneous. So it goes between 0.6, 0.5, 0.6, which is more or less evenly distributed. And that is, again, because of the combination of organic and inorganic. The partially hydrated shell, it's when we started saying lower electron density regions, that again is an indication of the presence of water or swollen organic material that becomes distributed around the sample. And the fully hydrated shell is really interesting because we see here now a separation between very low regions with very low electron density, which are these light blue ones, and some regions that have much higher electron density, which are predominantly the yellow. So what this is indicating is that to have organic material inside the shell in certain locations, in particular here, that are absorbing the water and they are swelling. We can see that a bit more quantitatively. So we can look at the average or the electron density distribution in the sample. So you see that in the vacuum dried, it sits around 0.6. This is the theoretical value of francolite is close to 0.8. So again, we have a mix of organic and inorganic, so we get an average. At 70% humidity, this distribution shifts a little bit to the left, but not much. But at 100% relative humidity is when we get this distribution changes completely, and we end up with 3 peaks, 2 of them at much lower electron density. So that is again indicating or showing how the shell is uptaking water and how the organic components are actually swelling. We can visualize that using a hydration map. So we can threshold the segmentation based on water content. And we see that the water is uptaken the same regions that we have the expansion. So we're talking about these areas here. And these regions here uptake slightly less water. And these regions here, which are highly electron dense, they uptake very little water. So they're composed mostly of the mineral. And this is now a thickness map where regions that contain water, higher water content, they become thick as well. So that is what we see, especially in this part here, but also in the regions, for example, this region here, which corresponds to this region here. So what this tachography is telling us is that at least on a micron scale, some regions of the shell that contain higher, possibly higher organic content, they are absorbing water and swelling. So we decided to look at this a little bit more closely. So we went back to scanning electron microscopy. We looked at polished sections that were either dried or they were hydrated and fixed before being polished. And what we see here in the dry shell is that we have some regions here that contain slightly more organic. So this is back scattered electrons imaging. So lower, darker regions means organic or more organic. And you see that these regions, especially here and here and here that contain some organic, the organic becomes much more prominent in the hydrated shell. So really you can see that the thickness of these layers, they seem to have increased. The other interesting bit is all these holes that we see here. and these are a network of pores that go through the shell, and we think that they may be involved in transporting water through the material. But that's our hypothesis. At least we see that they get filled with water again using ptychography. Looking a bit closer at the nanoscale against using SEM, we have here comparing dry shell and the hydrated shell. So the secondary electrons show that the structure is pretty much homogeneous, but when we use the backscatter electrons, we see that all those black regions that look like holes, they're actually organic that are intermixed with the mineral. These regions, these organic regions, they increase, they become slightly larger in the hydrated shell, which is where we see here. So this is indicating that we have the mineral organized in kind of bundles or rods that are surrounded by organic. And as the organic, which is absorbs water, they kind of swell, and the distance between these mineral rods or aggregates increases. And the last thing we wanted to do was go down another structural level and probe at the molecular level what water is doing. And for this, we resorted to solid state NMR. So that was collaboration with Professor Melinda Dewar from University of Cambridge. And what we observed is that when the shell is hydrated, we have the sharpening of a number of signals, in particular, the N-acetyl, methyl, and N-acetyl carbonyl groups from the chitin. And this is indicating that chitin, it's taking the water, the chains are becoming more mobile, and we're also getting water intercalated between the chitin and the shell, and the mineral, which could help to kind of weaken the interaction between chitin and the mineral, which could possibly allow the building blocks to move more freely. So based on these data, we developed a model to explain what water is doing to the shell and how that is changing its mechanical properties. And what we propose here is that in the dry shell, we have the mineral that is embedded in organic, and the mineral cannot move very much. It's bound to chitin sheets, which you see here in yellow between mineral bricks at the nanoscale. But the moment that the shell absorbs water, the organic components, they swell. Part of it is chitin. We increase the separation between mineral bundles, and we increase, and we kind of place water between chitin and the mineral. And all that together would allow the different building blocks of the shell to essentially move with respect to each other when you place a load. So it's as if pretty much water is acting as a plasticizer at the especially the nanoscale, which is not surprising because water is known to do that in many biominerals. So to conclude, we showed that the shells of Discinisca tenuis, they become flexible when they absorb water. They can bend, and they can bend in half without breaking. And we observed changes in the shell structure at 3 levels. One at the micron scale, where I have organic rich layers absorbing water and expanding. At the nanometer level, when the spacing between mineral building blocks increase, and molecular scale, where polysaccharide chains of chitin become more mobile. So last, I want to thank my group members, but especially also all the collaborators. The tachography was done at the Swiss Light Source, together with Johannes Hilli, Mirko Holler, and Klaus Vakoning, and all other collaborators that took part in the study, and of course, financial support. And thank you all for your attention.
Great. Thank you, Fabio. So